Okay, the next topic is our second pipeline in the algorithm. Okay, the name is called selective repeat. Okay, as we mentioned before, when we use go back and we have only one timer for the very first yellow segment in the window end, right? So every time when the timer times out and all the packet will be transmitted, no matter it arrives or it is not arrived at the receiver side. And we have cumulative egg, right? After that, people believe that retransmit packet using go back and is a little bit inefficient. So in selective repeat, we have different mechanism that receiver use individual acknowledgement to inform the user which packet arrives at the receiver side. So no cumulative acknowledgement used in select repeat, only individual acknowledge. And at the same time, for the sender, since we have individual acknowledgement, we have individual timeout as well. So every time when you send the packet out from the sender, okay, you have a set individual timer for each sending packet. Okay, so when the timer timeout, you only need to retransmit the exact unactive packet to the receiver. That is okay because we have individual egg, we have individual timer, when they have individual retransmission. So senders should maintain multiple timers for multiple packet. And again, we have a window to record all the packet that's sent to the receiver. So let's take a look at the view graph in this page. Okay, at the upper one is the sender's view, and the lower one is the receiver's view. So let's take a look at the sender's view first. Okay, in this case, we have the window starts at the 7th segment, right? So that means the sender already received egg 1, 2, 3, 4, 5, and 6. And in this window, the sender already sent 7, 8, 9, 10, 11, 12, and 13, 14 packet to the receiver. Since we currently in selective repeat, we have individual egg, right? So in this case, packet number 9, 10, 12, and 13, they are act individually. But for 7, 8, 11, and 14, they are yellow segment. They are sent, but they are not yet acted. Then the green one, 9, 10, 12, and 13, they are acted. So we mark it as green. And again, there should be a pointer called next segment number. They indicate number 15, 16, 17, and so on, and to 20. Those segments are ready to be sent, but they are not sent yet. And the buffer size is limited, so we only have a Windows size to segment number 20. Number 21, we don't have enough buffer to store the 21 segment. Okay, that is the sender's view. And as we can see that in the receiver's view, receivers also maintain a window size of n, right? And as we mentioned before, the receiver only needs to remember what is the next expected sequence number, right? So the receive base is right here, and it points to slot number 11. That means the receiver has already received data 2, 3, 4, 5, 6, 7, 8, 9, 10. And all those packets has been received, and all those X, X 2, 3, 4, 5, 6, 7, 8, 9, 10, has already been sent back to the sender, although the receiver does not know the packet of those ACK packets arrives at the sender or not, but it has been sent. So the window starts from 11. And as we can see that this receiver at this moment, it does not receive the D data 11, but it received the out of order packet number 12, 13, and 15. And again, number 14 is what it expected, but not yet received. Okay, but as an oracle, okay, you can see the sender's view and the receiver's view, and you can see that the base, the send base and the receive base is not exactly the same. So basically that means the receiver already sent egg number 7 and egg number 8 back to the sender, but the sender does not currently receive egg 7 and egg 8. So its window stop at slot number 7, not as same as the receiver. The window of the sender does not stop at slot number 11. So we can anticipate that maybe the egg 7 and egg 8 maybe it's delayed or it's lost in the internet. So that we can see that the yellow one, and anyways, we can see that, okay, the yellow with the black tint, it means the sender sent the packet, data packet, but it is not acted. But the receiver already act, but maybe it get lost in the internet. So at this moment, as we mentioned before, all the packet right here, all the packet has been sent. They should have a timer for every one of them. So eventually, maybe the timer of T7 and T8 will time out. Okay, and after you receive the egg, okay, you will remove the timer, right? So at this moment, only 4 timers will keep counting down, right? And sometime timer 6 and timer 7 and timer 8 will time out. So the sender will resend the data 7 and data 8 to do such kind of retransmission. However, when it arrives, the receiver simply just reply an egg and said, okay, I already sent the egg back, but if you want to confirm, and I will send the egg 7 and 8 again. So it makes the sender will move the window after it received the next expected packet 7, 8, 11, and 14. Okay, so that is it is much easier because we have individual egg, individual sequence number, individual timers, individual everything. So that is more simpler. However, you need to spend more memory, more resources to maintain all those buffers, all those timers, and so on and so forth. So right here, okay, sender data from the above. Okay, we will see if the window has enough slot to accept messages from the layer 7, right? So data from the above, if next available sequence number is in window, we send a packet. Okay, timeout, we have individual timeout, so we will resend the packet n if timer n times out, and we restart the timer. And we have individual egg, so if egg n is in the send base and the send base plus n, that means we receive egg, so we mark this packet as received. And if it is n smallest on x, if n smallest on x packet advance the window size based on the next on x sequence number, so then we move the window from the yellow one to the to the smallest yellow one. So for example, if we receive number 7 and number 8, and we can advance to number 11 because we have already received the egg of 9 and 10, right? So at the receiver side, it's very easy. Packet n in receive base and receive base n minus 1. That means I receive a packet, so we send the corresponding individual packet. If it's out of order, then we buffer. So one of an important difference between selective repeat and go back is that in selective repeat, the only implementation to deal with out of order packet is to buffer it. You cannot discard it because you already received it and you already add it, so you simply just buffer it. So if we receive an in order packet, then we deliver the buffered packets. Okay, if you have multiple buffered packets in order, and we advance the packet to the next not yet received packet, which is the red one. Okay, otherwise we simply just ignore it because everything is controlled by the individual act, individual timer, and the window. Okay, so here again, the example is exactly the same. Okay, the packet lost, the second packet, the packet number 2 is lost, but in this case we have individual act, so we can do individual act. So after we receive number 3, we simply just act 3. We have number 4, act 4, packet number 5, act number 5. So if packet number 2 right here, okay, there should be a timer T2, there should be a timer T1, there should be a timer T0. So every time when you send a packet, you set a timer. So after that, okay, packet T2 times out, and then we only need to resend packet number 2. We don't have to go back and because it is selected repeat. So after packet 2 arrives at the receiver side and packet 2, 3, 4, 5 will send to a layer 7 in order. And you have to notice that because we don't use cumulative, it is individual acknowledgement. So you only need to send act 2, not act 5 in selective repeat. Okay, so that is the selective repeat. The textbook does not have the final estimation of selective repeat, but I think it is good enough for you to understand the mechanism of selective repeat. Okay, and here we have a problem of selective repeat, but it will not happen in reality. It only happens when some very strange situation. Okay, take a look at this one. We have a very small sequence number, 0, 1, 2, 3. And then we have to reuse the sequence number, right? So again, we have 0, 1, 2, 3, 0, 1, 2, 3, so on and so forth. So relatively, our window size, n is 3, right? We have window size of 3. And the window size is a little bit large comparing to the sequence number. So sometimes when you send a packet out, okay, so when X goes back, right, the window size right here at the receiver side, sometimes they use off the sequence number, so I have to reuse the sequence number again. So 301, that means the receiver are waiting for the last sequence number 3 and reuse 0 and reuse 1, right? But when packet number 0 arrives, it is okay because it will when the receiver receives the packet 0, it knows, okay, this packet arrives, so it will mark it as arrived. right, and send the corresponding x0 back to. But this x0, right, this x0 and this x0, they are two different, although they both use this number 0, but they act different packet, right? But in this case, use receiver and the sender will not confuse which 0 is which 0, right? Because at the sender side, okay, at the sender side, right here, at the sender side, it acts the previous 0, and at the right hand side, the next act this 0, right? But sometimes, okay, if when you send the packet out, but all the packet are discarded by the network, so the receiver believes all the X goes back to the sender, but actually the sender does not receive all those X. So when receiver side, okay, it believes all the X has been sent, so it window advance to the next 0. But at the sender side, because all the X get lost, so at the sender side, its window stay at the very first 0. So meanwhile, when the 0x, okay, goes back, sender would, or the packet 0 goes to the right hand side. They do not at the same state, right? So they will get confused. But this situation can be solved by using a larger sequence number or smaller window size. So it can be easily solved in real world. So it only happens in the in textbook. But theoretically, we use a very, very large sequence number, which is good enough to solve this problem. Okay, so that is the next topic in select and repeat. Okay, so next few topics we're going to TCP. So again, we're to review some of the characteristics of TCP. The first one is point-to-point. We have one sender, we have one receiver in the TCP connection. Only 2, not 3, not 4, only 2, not 1. One is sender, the other is receiver. Okay, TCP provides reliable and in order byte stream. So basically, layer 7 can send any size of the message to the underlying layer 4 TCP protocol. So as we mentioned before, right here, okay, if I have a very large message, okay, and have several bytes from the first 0 byte, the index is start from 0, okay, the first byte is 0, second byte, third to the 1111 byte. Okay, so in total we have 1112 bytes received from the layer 7. And as we mentioned before, the TCP, the transport layer will segment, okay, segment those message into several different segments. For example, we have 4 segments right here, and I wrote the index of the byte of the first byte and the last byte. So the first segment, the first byte is the 0 is 0, and the last byte is number 200 bytes, and so on and so forth, so on and so forth. Okay, in the previous RDT and pipeline algorithm, we use segment number 1, 2, 3, 4, right, layer, right? But actually in TCP, the segment number is not 1, 2, 3, 4. The segment number used in the TCP is exactly the index in byte right here. So when I send segment, the first segment, okay, in TCP, I send this segment, and this segment is starts from right here. Start from the 0 byte from the perspective of the original MSG. And if I send the second segment and I say, okay, this second segment, it starts from the 201, which is an index, right, of the original message. So when I talk about sequence number, in reality, we use the number 201589901 to represent what is the first byte of this segment in the original message. We don't use the first or second or third sequence number. We don't use these numbers. Okay, so that is so basically you can send a very large layer 7 message. Okay, it can be thousands or billions or trillions of bytes, which is okay because we have a very large sequence number can be used to represent. And even if we use all the sequence number in bytes, okay, and we can further go back to use number 0, 1, 2, 3, and so on and so forth. Okay, so the second one is reliable in order byte string. TCP has no message boundaries, and the TCP is full duplex data. That means sender can send A can send data to B, B can send data back to A. It is bidirectional. But in later discussion, we simply just assign one of the peer is sender, the other one is receiver. But actually, A can send data to B, B can send data to A, which is full duplex. And here we want to introduce one thing is called maximum segment size. Actually, it is in bytes. So depending on different operating system you use, there should be a definition in your operating system to define what is the largest TCP segment size. Okay, so sometimes we say, okay, here is a segment, and it is the maximum segment size 1 MSS. Okay, so make sure you know the terminology. Okay, right hand side, TCP use cumulative X, but the cumulative X is not like what we introduced in the go back N. It is a little bit different. We'll talk about later. Okay, and TCP has pipelining. Okay, so that it can so TCP has higher performance than stop and wait mechanism. Okay, it is oriented connection oriented. That means before we exchange real MSG message, two operating systems need to exchange certain parameters among to each other to exchange. For example, what is your window size? What is my window size? What is the sequence number that we use? So on and so forth. Tons of messages need to be exchanged before you send that message. So we'll talk about later. Okay, so we have congestion control, we have flow control, so that the TCP sender will not overwhelm the receiver, and TCP sender will not congest the routers on the routing path. Okay, we will talk about everything in this page later. Okay, more in detail. Okay, so here, that is the TCP segment structure. So right here, as you can see, that is an TCP segment, and of course at the right hand side we have layer 4 headers, and we have layer 7 payload, right? So you can see, you can think that if it is HTTP layer 7 message, the word get, GET, will be right here in this at this place, very first byte. Okay, so that is the layer 7 part. Okay, and you can see that the width of this structure is 32 bits. Okay, you have to know that 132 bits equals to 1 word. Okay, 1 word. Okay, that's the definition. So basically, when you receive a TCP segment, okay, you simply just read the first 16 bits, right? And parse it, okay, fetch the first 16 bit and view it as an integer, and then it will be a number between 0 to 65535, right? So that is the source port, and the second 16 bit is the destination port, okay? And the next 32 bit is the sequence number, and the next 32 bit is the acknowledge number. So as I mentioned before, in TCP we don't use the integer, the consecutive integer to represent the first sequence number, the second. No, we simply just use the byte, okay, the index of byte to represent. So for example, if it is the very first segment of your layer 7 message, theoretically the sequence number should be 0 at the very first segment that you transmit the layer 7 message. But it is theoretically. We will talk about some algorithm and some rules how to define the sequence number, okay? The acknowledgement number is the same, but it uses the third row, okay, at in the header, okay, that is the ACK sequence number, okay? The fourth row right here is a little bit complex, okay? Here we have a receive window, okay, it is 16-bit, right? So here we have 8 control bits right here, and we have 4 bits for the header length, and 4 bit is not used. Okay, so the header length has 4 bits, right? Usually it is an integer in this 4-bit field, and it usually is 5. 5 means how long the length of the TCP header. 5 means this header is 5 words long. So as we mentioned before, 1 word equals to 32 bits. So 5 words means 116 bits. That is 20 bytes. Okay, so the definition is a little bit different. We use words in this head length field. So usually it is 5. So that means we have 5 words. Okay, the reason why we have such kind of header length is because TCP indeed has optional headers. Okay, so it could be variable length. So you have to specify how many words are there in your TCP header. But basically, most of the time, we have no options. So we have only 5 fixed field headers right here. So we only have 5 rows, 5 words, or 20 bytes, or 116 bits. Okay. But if you have additional options, headers in your TCP header, so you can specify, okay, I have 6 rows, which means 6 words in your header. So we have 5 fixed and 1 additional option. So it depends on how many headers you have. But actually, as I mentioned before, usually we don't have optional headers in our TCP headers. Okay, so next one is right here. We have 8 control bit. Okay, CEUP. Okay, these 4 we seldom. For example, a C and E, they are used for conjunction, and U is for agent. So it's urgent right here. U stands for urgent. Okay, C and E we'll talk about later. P stands for push. Okay, we will talk about how they work later. Okay, basically, but we seldom discuss about them because they're not that important than the others. Okay, the other four, A, R, S, and A, they are more important. A stands for egg. Okay, R is reset. S, synchronization. F means finish. Okay, so those four control bits is much more important than the other fours because they are critical for you to do acknowledgement. So if this segment is an acknowledgement, you have to set this bit, A bit, to 1, and you have to set appropriate corresponding acknowledgement number right there. Okay, but if it is a data packet, you set this A bit to 0, and the acknowledgement number is meaningless, and you have to set your corresponding sequence number because it is a data packet, right? So for R, S, and A, that means two operating systems, they are trying to exchange exchange parameters before sending real message, right? We have to do connection setup, right? So S is for synchronization. Sender and the receiver should come up several parameters and exchange certain settings. So they will set sync bit when they do such kind of synchronization. So after they send messages, when the sender and the receiver would like to terminate this TCP connection, they have to use the fin bit to inform the sender or receiver, say, okay, I would like to terminate this TCP connection. So this bit will be set. Okay, so receiver window, we will talk about receiver window later. Okay. So next one is checksum. It is similar to the checksum in UDP. Okay, similar to UDP. And then optional, we'll talk about optional later. So that is the TCP architecture, segment architecture right here. Okay, make sure you understand every bit, but don't worry about it because we'll talk about every details in the later class, okay, in next week. Okay, so I think we can stop right here because next few video graph is secret summary is a little bit complex. So we stop right here. Make sure you check the website every week. So we will announce the homework, announce the, for example, the midterm example. Okay, so make sure you check out those websites every week. Okay, that's all.